Okay, in this video I'm going to demonstrate a few strategies for dealing with missing data when running structural equation modeling through the AMOS program. Uh, the demonstration is going to pivot off of this path model right here, where I have performance goals, mastery as exogenous variables, and anxiety, achievement, and interest as endogenous variables in the model. The data are contained in this file right here, and so you can see that I have each of my measured variables, and then the blank cells are reflecting missing data. So basically, once you've drawn out your model and you've gone through the process of importing your data into the program, the next step is going to be to go to Analysis Properties, click on it, and it's under this set of properties right here that you can ask for various outputs and specify certain types of analyses. So the first thing that you have to do if you want your model to actually run is you have to click on Estimate Means and Intercepts. So if you have missing data and you do not click on Estimate Means and Intercepts, then you're going to get an error message and the model's not going to run. So just to demonstrate what I'm talking about, I'll click off and I'll just go over to Calculate Estimates and click, and so you can see that I end up with an error message. So it just says, in order to analyze data with missing observations, you must explicitly estimate means and intercepts. So, so that's what we're going to do. We're going to click on this, and so now if I run the model, I get no error message and everything comes out okay. Under output, I can click on things like standardized estimates, squared multiple correlations. If I'm doing a path analysis, I'll generally click on indirect, direct, and total effects. And there are other things that I could click on so to get that kind of output. So one of the things to note with this, so let's just run the analysis. I'm going to click on Calculate Estimates, and now I've run the analysis. And when I click on this button right here, and look at it, you can see there's a little toggle over here for unstandardized estimates and standardized estimates. So these are essentially unstandardized regression coefficients. This over here would be the covariance between performance goals and mastery goals, and so forth. If I click on standardized estimates, these are essentially interpreted as beta weights. So these are standardized regression coefficients, and then this would be the correlation between performance goals and mastery goals. So when I look under the View Text option, we can look at the general model fit, and so the model fit statistics are used to evaluate the fit of your model to the data. So you can see that we have a number of different fit statistics that are printed out in this summary right here. Up here we have the chi-square goodness of fit test, which is interpreted as an indicator of the degree of, really, the degree of badness of fit. So you can see right here we have a p-value that's 0.866, and really what that's doing is what you're testing is the difference between the model implied covariance matrix and the sample covariance matrix. And so the null hypothesis is that the elements within these two matrices are equal. So the alternative hypothesis, there's sigma and there's the S matrix, and the alternative hypothesis is that they're not equal. So if the p-value is indicating non-significance, as it is right here, the conventional p-value is 0.05. In this case, we are actually observing a circumstance where the model implied covariance matrix is consistent with the sample covariance matrix, and what that means is that we end up maintaining the null hypothesis. So this is actually an indicator of good model fit to the data. So the downside of this particular index, or this particular test, is that it is impacted by sample size, and given that SEM is a large sample technique, it's very easy to end up rejecting the null hypothesis, even with fairly small deviations between the two matrices. So for that reason, we oftentimes will consult other types of fit indices in order to make a judgment, so more descriptive indices. So for example, there's the CFI right here, the Tucker-Lewis, which is also referred to as the non-norm fit index, the RMSEA down here you can see, and so forth. So there are various ones. So just to kind of give you a little idea about what to look for, from this book right here, this is a nice little table containing model fit criteria and what constitutes acceptable level. So you can see the chi-square value. This is just that chi-square goodness of fit test. We don't have these indices printed out in our current output, but we do have the RMSEA, and so within this particular description right here, what we're looking for are values that are smaller. So basically values that are acceptable would be between 0.05 to 0.08. Values less than 0.05, between 0 and 0.05, would be considered much closer fits. So we can see based on our output, looking at it, if I can kind of find it here, you can see the RMSEA value was 0. So basically that's indicating that we have good model fit to the data. We can also look at the Tucker-Lewis index. So basically it ranges between 0 to 1, where values that are higher are indicating better fit. The same would go for the CFI. And so for those two indices, we're really looking for values that are falling at least at 0.90 or above, although the description in this text right here suggests values close to 0.90 or 0.95 would represent a good model fit. So if we look at our output right here, you can see the CFI is 1. You can see this TLI is actually a little bit higher than 1, but for all practical purposes, we would just treat this as 1. And so in general, it looks like, based on some of those fit indices, that we have evidence of a good model fit to the data. If we look under estimates, we have the unstandardized path coefficients, which are reflected right here. These are the regression coefficients. We have the standard errors for those regression coefficients. The CR is essentially taking the ratio of the estimate to the standard error. So given that this is a large sample technique, generally these are going to be interpreted as z-values, and then we have a p-value associated with our tests. And so the 3 asterisks is just rounded off, so if you were reporting this, you would report it as p less than 0.001. So you can see that mastery to interest, that was a significant predictor. It was a significant positive predictor. Mastery to anxiety was a significant negative predictor. There's a negative. Performance goals to anxiety was positively related, but it was not significantly related. So this was non-significant here. So we'll just take, that's non-significant. Performance goals to interest was also non-significant. Performance goals to achieve, basically a slight negative relationship. It wouldn't be conventional at the 0.05 level with the two-tailed tests. And then you can see anxiety to achievement wasn't significant, but interest to achievement was, and so was mastery. So the coefficients that you see within this table under estimates are essentially, if we go under unstandardized estimates, these are the same values that we see within the figure. The 0.00 right here is just rounded off at 2 decimal places, but it's not actually 0. Then, if we scroll down a little bit further, we've got the standardized path coefficients or standardized regression weights. So these are all the estimates. And so in this particular case, these are going to be the same values as you see if we go under standardized estimates right here. You can also see that if we scroll down further, you can see we have our matrices for total effects. These are unstandardized, standardized total effects, direct effects, standardized direct effects, and so forth. and then the R-square values are contained in this matrix right here. So the predictors of anxiety accounted for about almost 11% of the variance. The predictors of interest accounted for about 39%. The predictors of achievement accounted for about 40% of the variation. So the thing to keep in mind when you are running your analysis is that, like I said, in order to, if we have missing data, in order to run our analysis, we had to click under Estimate Means and Intercepts. Now, at this point, you might be interested in perhaps it may be the case that you want to tweak a model or modify it in some way in order to improve its fit. And so oftentimes we rely on the modification indices option, which is this right here. The downside of this analysis at this point is that the modification indices only work if you have a complete data set, meaning that there's no missing data. So if I click on this, for instance, and I try to run the analysis, I end up with an error message, and it says, modification indices cannot be computed with incomplete data. So you can't generate modification indices if you have missing data. So that's a downside. Also, if you wanted to perform some type of bootstrap, like if you wanted to generate bootstrap confidence intervals and standard errors and confidence intervals associated with the estimates in your model, then you also require a complete data set. And oftentimes researchers, particularly when they're running a path analysis with either measured variables or latent variables, they want to test the indirect effects within the model, or basically the mediated effects. And to do that, you have to use bootstrapping. And so if you try to perform bootstrapping, though, and you have missing data, then that's going to create a problem. So I'll just demonstrate. Let's say I'm going to click on Perform Bootstrap. Let's say I'm going to ask for bias-corrected intervals. I'll even increase the number of bootstrap samples just for fun. And when I click on the Calculate Estimates, you can see it says that an error occurred and a bootstrap can't be performed with missing data. So basically that prevents you from being able to run the analysis that you want to run. So if you have missing data, that creates a real problem in terms of being able to get things like modification indices or generate bootstrap standard errors and confidence intervals. So one thing that you can do is to utilize an imputation strategy. So AMOS does have imputation options. Probably the simplest approach is to go to Analyze, go down to Data Imputation, and click on this button right here. So the thing about it is that you have to draw out your model first and have your data already input into the program. And once you've done that, if you just go up here again to Analyze and go to Data Imputation, you actually have several options. You've got Regression Imputation, Stochastic Regression, and Bayesian Imputation. And I'm going to stick with just the Regression Imputation in this particular demonstration, although the other two options are available to you, and I'll let you consult the AMOS manual for that. But basically, what's going to happen is that when I click on Impute right here, it's going to generate a new data set that's essentially imputing values on your missing variables, and it's based off of the maximum likelihood estimates that are generated for your model. So what I'll do at this point is I'm going to click on Impute, and so now it says the following completed data file was created. It actually gives me the name right here. It's just path analysis, right here, path analysis incomplete data _c.save. So it's basically saved into an SPSS file. I'll click on OK, and now I'm just going to click out of here, and then let's see if there was anything else I needed to click on. I think that was it. So at this point, I'm going to go over here to the Select Data Files, click on it, and then go to File Name. And so you can see that this is it right here. This is the new data file with the imputed values. So I'm going to click on Open, And so now, just if you want to take a look at it, we'll click on View Data. And so now you can see that there are no missing values in the data set. So we've generated imputed values on our variables. And so now we have a complete data set. And so at this point, now we can go back into our program, and we don't really actually need now to have our estimation set at estimate means and intercepts. It doesn't really matter one way or the other if we do or not, but I'm just going to click off of that and go to output. And so now I can click on modification indices if I want. Under Bootstrap, I can also click on perform Bootstrap, bias corrected confidence intervals. And now when I click on the calculate estimates, it works. So if I, again, these are all the estimates, the unstandardized estimates, standardized estimates as pretty much before. The data set, in the analyses in many respects are going to pretty much mirror what we had before when we were just using the full information approach with the missing data. So under model fit, you can see that pretty much we had the same results for all of these indices right here. The RMSEA is still good here, and you can see now modification indices. There were no suggestions in terms of improving the model fit, but you can see that had there been any suggestions, they would have appeared under this modification indices option right here. You can also see that you have bootstrap distributions and summary of bootstraps and so forth. But if you want to look at the bootstrapped standard errors and confidence intervals, then click under estimates right here. And notice, right now we're right back to where we were before with the regression weights and so forth. Down here it's not highlighted yet, but you can see it says estimates, bootstrap estimates, bootstrap standard errors, and confidence intervals. And so now if I want, these estimates right here and the test of these estimates are all based on normal theory method. But if I wanted to access the bootstrap confidence intervals for each of these estimates, I could do this. If I click under scalars right here, you can see regression weights. And so now when I click on that, you can see that these options all highlight. And essentially, if I want to, let's say I want to test the relationship between mastery and interest using the bootstrap bias corrected confidence intervals. The estimate is 0.751, and I can click on bootstrap confidence down here, and you can see that now I've got, it says, the regression weights. Here's my estimate. This is the lower bound and the upper bound of that confidence interval. I think that in the demonstration when I was running this, I think that I had set this, I left it on the default. It was for a 90% confidence interval. If I wanted to raise this, I certainly could. So if I wanted to use 95%, I could. But the default for some reason in AMOS is the 90%. So but like I said, if I want the 95%, I can certainly do that. Let's just do it. So now I've run it with the 95% confidence intervals instead. And so going back to the estimates and the scalars and the regression weights, and then down here for the confidence intervals. Now these are 95% confidence intervals that are based on the bootstrap standard errors. And so the interval is formed around that estimate right here. If you actually want to see the bootstrap standard errors, you can look right here, and here they are. So there's the standard error and so forth. So at any rate, there you go. So if you want to look at, let's say you want to look at the standardized regression weights, you can also get, the bootstrapped confidence intervals around the standardized weights. The same for the covariances right here. They're the lower and upper bound correlations. Even the squared multiple correlations, or the R-square value, so you can test those out. In this case, using this particular method. If you go under matrices, you can see that we have total effects and direct and indirect effects. So if I want to look at the indirect effect, like, kind of going back to our model, let's say I want to look at the indirect effect of mastery goals on achievement. Well, we have an indirect effect of mastery on achievement through this route right here. We also have an indirect effect through anxiety to achievement through this route. So we have essentially two indirect effects, and they would sum up to essentially a total indirect effect. So I'll just call it a TIE for short. So it's a total indirect effect. Unfortunately, AMOS does not allow you to let's say this is path A and this is path B, and let's say that this is path C and path D. When you're computing the indirect effect, a given indirect effect through a series of paths, an indirect effect is just simply taking path A and multiplying it by path B, like if we're going this route right here through anxiety. If we want the indirect effect of mastery on achievement through interest, then it would be essentially path C times path D, so to get this indirect effect. And unfortunately, AMOS doesn't provide a test of each individual mediated relationship. So the indirect effect that is printed out is actually computed by summing these two indirect effects together into that total indirect effect that I was telling you about. But nevertheless, you can still go in and you can see the use the bootstrapped standard errors and confidence intervals in order to test the total indirect effect. So I'll go back under estimates, go under matrices, go to indirect effects right here, and so you can see that the indirect effect of mastery, or the total indirect effect of mastery on achievement, this is the unstandardized indirect effect, by the way, is 0.160. And if I want to look at the 95% confidence interval, I can click on Bootstrap right here and the bias corrected percentile method, and you can see now you've got the lower bound of the confidence interval and the upper bound. So previously, when we're looking at using the scalars right here, you had the lower bound and the upper bound kind of in the same row. Here it's offset into two separate tables for each element. So you got mastery and achievement. This is the lower bound of the 95% confidence interval that we computed, and then the upper bound is there's mastery and achievement, and the upper bound is 0.299. So and you can essentially test whether the null indirect effect, the null indirect effect would be that it's equal to 0, and so if 0 falls between the lower bound and the upper bound, then you would maintain the null and conclude that there's no significant indirect effect. If 0 falls below the lower bound or above the upper bound, then in that case you would reject the null and conclude that the indirect effect, or the total indirect effect, is significantly different from 0. So another option, if you don't want to look at it using the confidence interval approach, you can also, there's a table right here that contains p-values. So you got mastery and achievement, and so this would be the p-value that you would associate with that it would be used in testing the significance of the indirect effect that we computed. So once again, the indirect effect was 0.160. If we use the confidence interval approach, the lower bound is 0.06, the upper bound is 0.299, so 0 doesn't fall between the lower and the upper bound, so we would reject the null. Or if you wanted to use the p-value instead, you can see it's 0.005, which would be less than the conventional 0.05 level for rejecting the null. You can also see that for performance goals, I'm going to click on estimates, go back, and you can see that the indirect effect for performance goals on achievement is negative 0.002. And if we look at our bias corrected method right here, you can see that with performance goals the lower bound for the 95% confidence interval is -0.008. The upper bound is 0.001. The null hypothesis, again, is that the indirect effect is equal to 0, and so 0 falls between the lower and the upper bound, so you would maintain the null. Or if you wanted to report on a p-value for the indirect effect, remember it was -0.002, you could use the p-value that's printed out right here, which is the 0.144. So that pretty well sums up a lot of what I wanted to talk about in dealing with missing data. So just keep in mind that if you have missing data in the AMOS program, at a minimum, if you're not going to ask for things like confidence intervals, or you don't want anything related to modification indices and so forth, and you have missing data, a file that contains missing data that you're feeding into the program, you have to click on Estimate Means and Intercepts, and that will at least get you a full information, maximum likelihood estimation of the parameters in your model, and it will generate the fit statistics and so forth. But if you want to use modification indices or perform any kind of bootstrapping or anything of that nature, then you have to have a complete data set in order to be able to do that. So in order to obtain that complete data set, one option is just to go through the Analyze button right here, go to Data Imputation, and you can use the Regression Imputation to generate a new data set, and then go in, and once you've generated that data set and imputed the values for it, then you can essentially go into go in here, select the data file that contains it. Then you would have a complete data set, and then you can specify whether you want modification indices or you want the bootstrapping options available to you. So that pretty well concludes this demonstration. I do want to point out that I have not gone into kind of the theories behind missing data, or the limitations of this particular approach to dealing with missing data. I'll leave that to you because there's just not enough time to do that. But basically, it would be worth your while to follow up and kind of read up on the issue of missing data and different treatments. This is obviously one strategy for dealing with missing data. There are other types of strategies that are possible, but all of them, make assumptions about the missing data mechanisms, and so you want to be careful to utilize the best strategies possible for when your data are missing. So that concludes this discussion.